Okay, so the big thing that I'm going to be talking about in this page is actually where they get this from. But let's quickly talk about everything else, I guess. All right, incidence is obviously number of new cases divided by number of people at risk. So if you've got 100 people in a population and it remains static, okay, in 1 year 50% of people are affected, and the next year 10 people are affected, then the incidence would be 10 over 50. It wouldn't be 10 over 100 because of the original 100, 50 were already taken, and for that year you have 50 who are at risk. So again, different example, if you had 20 people in 1 year, 10 of them are affected by disease, and then the next year 5 of them are affected, the incidence would be 5 over 10. And prevalence equals number of cases over total number of people at a point in time. Okay. Obviously, if you increase the survival time, you're going to have more prevalence. Right? It's the reason why HIV, well, it's one of the reasons why HIV now is more prevalent than it was before. People used to die really quickly, and now you have life-saving drugs that people can live a normal life on, as long as they take this drug every single day. Increased mortality, you're going to decrease your prevalence, obviously, because you're going to have fewer people. And the denominator here is total number of people. And you're going to mess up the existing cases. So anyway, faster recovery time, same thing, prevalence is going to go down because you're not going to have as many cases. Bunch of vaccines, again, you won't have as many cases, prevalence goes down. Also, incidence will go down because people won't get it. And you decrease the risk factors, people won't get it. Incidence will go down, and it won't last as long, and it won't be as prevalent. All right. Precision and accuracy. Accuracy has to do with relationship to the gold standard. Precision means how often can you get the same result over and over and over again. All right. So suppose you're supposed to get, I don't know, the number 5, and you keep getting the number 2, a million times. It'd be very precise. It would not be accurate. Okay. And the next page we'll go over things like statistical power, deviation, and all that kind of stuff. But now I want to focus on this. Prevalence equals 1 minus prevalence, or prevalence divided by 1 minus prevalence equals incidence times, duration, what's going on, blah, 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 blah. Where do they get this stuff from? So the best way to think about this, and I made a big old thing here, is you can think about it as the prevalence odds. Meaning the odds of finding someone with a disease compared to the odds of finding someone without a disease. Alright? It'll be greater if you have a disease that lasts forever or has a very high incidence. That's all you got to think of, okay? You have a disease out there, and let's say it lasts, a second. Well, the prevalence is going to be tough because you're not going to be able to really find someone if the disease lasts a second. But for something like diabetes where it lasts forever, well, then the odds of finding someone with that disease is going to be much greater than finding it without the disease. So I would actually rephrase this as just saying the prevalence odds, meaning the odds of finding someone with a disease compared to without the disease. And that, of course, will be influenced by how high the incidence is, and, of course, by how long the duration is. Okay. So here's the next level, okay? Where are they getting P divided by 1 minus P from? What the heck is going on here? All right, well, what's the implication of this image down below with the bathtub? And it has to do with how they ended up deriving this. Okay. So in this situation, you have a population, and this population has n people, and you can look at the bathtub for an example, or you can just think of this thing in your head, okay? But this will kind of also act as a nice little addition to whatever you're thinking about. So you have a population with n people, and the population is constant. You can see the incidence, people going in equals people coming out, right? And there's no immigration or emigration, though, in this one population. All right, so the people are just either reproducing or dying. All right, so of these n people, P of them have a disease. And the number of people who have a disease is constant. So again, the new people are getting it or they're dying. And the people who are dying are being replaced by people who are getting it. All right, so this is just the setup here. So the people entering this prevalence pool is equal to, of course, the incidence, which is people per time, all right, multiplied by the people at risk, which is the total number of people in the population minus the amount of people who actually have the disease. All right, times however much time you're thinking about, okay? If you're saying people entering the prevalence pool over 5 days, well, then multiply by 5 days, all right? But the idea here is that you have a certain amount of people entering the prevalence pool, and it's equal to the incidence times the number of people at risk times, of course, the time that you're giving them. Right, and at the same rate, and at the same token, you also have people exiting the prevalence pool. Right, same here, people going in, people are exiting the prevalence pool in a little bathtub example. All right. Well, the people exiting the prevalence pool is actually going to be equal to the people, the people exiting the prevalence pool equals the incidence of the people exiting the prevalence pool times the time times the prevalence. Right, and you'll see how it's very similar to our first equation of people entering the prevalence pool. The only difference here is that you're not multiplying by n minus p, because here you're already assuming that, of course, everyone in it is already in the prevalence pool, so there's no need to do n minus p, you can just do p. Okay, so just one more time here. You have people entering the prevalence pool, and you have people exiting the prevalence pool. And an important thing to keep in mind is how the number of people who have the disease is constant. So, with that, we know that people entering the prevalence pool is going to have to equal people exiting the prevalence pool. Okay, so now I'm just setting the two equations that I had here, a little bit up here, here we go, equal to each other. So the incidence, get the total number of people, minus p to get the number of people who are at risk, times time equals the incidence of people exiting the prevalence pool times the time, times the prevalence pool. And prevalence pool is the number of people, because prevalence, again, is cases per, population. It's not a number, whereas the prevalence pool is a number. All right, cool. And so I'm just rewriting this top equation here as this thing down here. I'm just simplifying it a little bit. As the inflow of n minus p times time is equal to the outflow times p times time. Of course, this can be simplified by crossing out your times. All right. And now we're left with the inflow is equal to the, inflow n minus p, people at risk, is equal to the outflow times the prevalence pool. And so here's the cool little thing you have to keep in mind. All right, this is where everything starts getting tied together. We have no population migration in this population, remember. So the outflow incidence is equal to the reciprocal of the disease duration. Think of it like this a little bit. If you have 5 cases per year, that's the same thing as 1 case every 0.2 years. Okay, similarly, if you had 10 cases per year, that'd be the same thing as 1 case every 0.1 years. Pretty straightforward. So now we can actually end up replacing the outflow incidence with the reciprocal of the disease duration. So let's do that. So now you get the inflow, or incidence, whatever you want to call it, times n minus p is equal to 1 over the average duration times p. And of course, when you multiply, bring d over, and subtract by n minus p, you get incidence times duration equal to p over n minus p. So you can already see how this is really similar to that first equation that we had over here. P over 1 minus P equals incidence time duration. But there's only a few loose ends to tie up. And if you want to stop now, that's great. No one's going to blame you for it, okay? But remember that P over N minus P is the ratio of the diseased to the non-diseased. Okay? Because remember, here, this is the people who have something. And this is the people who are just at risk. They don't have it, but they're at risk. Because in this situation, you either have something or you're at risk for having it. Okay? So this is the ratio of the diseased to the non-diseased. Or you can think of it as the ratio of the proportion of the prevalence to 1 minus the prevalence proportion. P. 1 minus P. How cool is that? So that's just if you wanted to have the nitty-gritty and the lowdown on how all of this stuff worked, how everything was going on. But another good way of just thinking about it, in case you don't have the time or don't particularly care, is you can think of this as just the prevalence odds. What are the odds of finding someone with the disease compared to not finding them with the disease? And again, if the disease lasts forever and has a high incidence, then those odds will be greater.